Okay, so in this final video, I want to bring everything together. And I want to start again at the beginning with what we did at the beginning when we talked about this example with the cookies. So if you remember, we started out by saying, okay, the cookies we can have 0, 1, 2, 3, 4, or 5, and then the total utility was 0, 5, 9, 12, 14, 15, and the marginal utility was, we don't have here 1, but then it was 5, 4, 3, 2, 1. And then if the cost for a cookie was $2, we said it is economically rational to consume cookies as long as the marginal utility is greater than the marginal cost. The marginal cost is always $2 per cookie. And so then we developed a graph where we had here the cookies, let's call it again X. And here we had now the marginal utility. So we had here 4, 5, 3, 2, 1. And we derived the marginal utility function, which was a straight line, and the marginal cost was always 2. And then we said the optimum consumption is where marginal utility equals marginal cost, because at this point we get all that extra surplus, and at the point where the marginal utility equals marginal cost, that is where you have the profit maximizing quantity. So marginal utility equals marginal cost. That is what we already derived intuitively. The only difference now is that we have a more formal environment and we use functions. So here we have a total cost function and the utility function, which are the ones that we already derived earlier. But building on the same logic that I just introduced here, we now know that as long as the total utility is greater than the total cost, we will consume. Or, alternatively, as long as the marginal utility is greater than the marginal cost, we will consume. And the optimum will be where the marginal utility equals marginal cost. So basically, finding this point. But now we have a more complex total cost function, namely an inversely related one, and we have a concave utility function. Okay, but what we need to do is, in order to solve the optimum, we need to find where the marginal utility equals to the marginal cost. Okay, so let's first derive again the marginal utility. And we said, okay, let's just do it again one more time. So this is 16 times x raised to the 1/2. And then again, we took the 1/2, put it in front, and then we subtracted 1. So now we get 1/2 times 16 times x raised to the 1/2 minus 1, which is then 8 times x raised to the negative 1/2, or 8 over the square root of x. So that's the marginal utility. The marginal cost function, we already did that also, so the 3 goes in front, so I'll have 0.15 x squared minus, okay, 2 goes in front, so 1.5 x. So we have to subtract again the 1 plus, there's this invisible 1 times 4, so that is only plus 4. Okay, so they need to be equal. So now I would have to solve an equation where, so we need to solve where 8 over the square root of x equals 0.15 x squared minus 1.5x plus 4. So that's supposed to be a 4 here, 4. And so here, this is the marginal utility, and this is the marginal cost. We have already drawn those functions, so we can put them into one graph. So we have here the marginal utility, and the marginal utility was a function that looked something like this. And the marginal cost, let's give that a different color, that was a function that looked also something like this. So there should be a point where the marginal cost equals the marginal utility, and that optimum x, which we like to call x star, because that's the optimum, the star means the optimum, requires solving that equation. But this is obviously a very complicated equation, and I'm not very good in math either. But the good thing is, we can solve that equation easily in Excel. And also in Excel, what we can do is we can draw those graphs and first look at the solution, maybe graphically, and then we can solve it with Excel, but I do that in the next video.